Hi, I'm Amir Zamir. This paper is joint work with Alexander Sachs, Nikhil Cheerla, Rohan Suri, Zhangjie Cao, Jitendra Malik, and Leonidas. In practice, we are often interested in making multiple predictions given an image. For example, normals, objects, depth, and so on. A common solution is to independently train neural networks for each of these tasks, which leads to results that are often inconsistent with each other. For example, you can see in these magnified windows that depth and normals clearly have not recovered the same 3D shape. This paper proposes a method for addressing this general issue through cross-task consistent learning. We show that learning with cross-task consistency fits the data better and makes more accurate predictions, gives model with better generalization and more consistent predictions, and also it leads to an informative intrinsic quantity, which we call consistency energy. Our method documents a standard supervised learning objective with cross-task consistency constraints. It's a fully computational and rather general method. The constraints are completely learned from the data, so there's no need to assume task relationships are known or differentiable. Here's a high-level overview of the method. As an elementary case, suppose X is the query domain and Y1 and Y2 are two domains you're interested in predicting. The standard supervised learning trains a neural network F for domain Y1 and trains another network G for domain Y2. We introduce an additional constraint to this objective, here shown using the function H. This is a cross-task function that relates domain Y1 and Y2 and cross-checks them against each other. This way, learning Y1 and Y2 are not independent anymore. These cross-task functions are neural network themselves, and we automatically learn them from the data. Here's an intuitive qualitative example. X is RGB image, and Y1 and Y2 are depth and surface normals. If you learn to predict depth independent of normals, then infer normals out of it, the results show a lot of inaccuracies. While if you learn depth subject to a consistency constraint with normals, not only the deduced normals look much better, but the depth prediction itself gets improved too. This is an intuitive and small scale example. We extend this concept to any arbitrary pairs of tasks with obscure or unknown relationships. Now, the triangle is the most elementary unit of a cross-task consistent system. It operates over only 3 domains. When we have a large dictionary of tasks, first we show that the triangle constraint can be extended to the more general path invariance constraint. Then in the paper, we discuss how we can efficiently optimize for a globally cross-task consistent system, which satisfies the consistency constraint for all feasible paths in task graph. Finally, we define the consistency energy. The inconsistency in the system can be quantified by measuring disagreement among the outputs of different prediction paths. We define consistency energy as the total amount of disagreement in the predictions made for one query. The lower the disagreement, the lower the energy. We performed experiments on multiple datasets shown here, including Taskonomy and Replica, and also CocoDoom and ApolloScape as out-of-training distribution datasets. We compare against a standard independent learning, which is the main baseline, multitask learning, which predicts multiple tasks out of one image using a shared encoder, cycle, which is a special case of enforcing consistency between 2 domains, assuming digestion, and average estimator control baseline. We also compare with conditional GAN models and GeoNet, which is an example of a curated consistent learning based on known analytical relationships. Here's a qualitative comparison for several prediction domains. You can see that consistency notably improved the results, especially in the fine-grained details like in the yellow markers. And this is the corresponding pixel-wise consistency energy. You can see that the high energy areas usually correlate with the challenging and error-prone parts of the image. Here are sample results of testing the models on images that are far from the training data distribution. You can qualitatively see that the models continue to perform reasonably well, and you can see the paper for the quantitative analysis of generalization. We also have a live demo webpage where you can upload an image yourself and receive the prediction results. And here we compare with the baselines. Again, we defer the quantitative analysis to the paper, and you can also run a similar comparison on the demo webpage. And finally, here are some utilities of the consistency energy. First, this plot shows the amount of inconsistency among predictions indeed drops to a low value for the consistency model. This plot shows there is a good correlation between the energy and supervised error, which suggests the energy can be used as a confidence estimation. And these 2 plots show the energy versus various domain shifts, which again suggests the energy can be used as an empirical indicator of domain shift and uncertainty. Thank you very much, and you can find the code and train models on the project webpage.